Hello, my dear students, and welcome to our last lecture with the selected topics in electronics engineering module as a module delivered for senior students. Maybe in the last lecture, in the previous lecture, we have discussed together the concept of capacitance associated with the logic gates, in terms of an input capacitance or in terms of an output capacitance. And our main consideration today will be how these capacitance are going to affect the operation of the logic gates. Also, we are going to highlight the effect of the sizing, how we make a sizing for the transistor in a CMOS logic gate, and the impact of this sizing on the value of the capacitance, and then in the value of the overall equivalent capacitance associated with the logic gates. So, in order to start this process, let's first start with what is a capacitance. As you simply know, the most simple model for a capacitance is what we can call a parallel plate. I'm sorry, I'm just opening my laser pointer. So what we call a parallel plate capacitor. A parallel plate capacitor is a capacitor that consists of a electrical material sandwiched between two conducting metals, where there is a voltage applied. In this context, the process of having a charging or discharging capacitor starts to occur. And here, the process of charging or discharging is mainly associated with time. So, in terms of equations, we can say that the capacitance equals to Q over V, where Q is the charge and V is the voltage. Or in other words, we can say that Q equals CV. In the same time, we know that charge or the current is the rate of a change of a charge. So it's dQ by dt. Using this information, so we can say that I equals C dV by dt, which is, I think, a very famous equation linking between the current and the capacitance in terms of the rate of change of the voltage. In this equation, we can say that current is linearly related to the capacitance, and the slope of this relation is the dV by dt, or in other words, the rate of a change of voltage, which is either a positive dV by dt in a positive manner, giving us a charging process, or dV by dt in a negative manner, considering a discharging process. So, generally speaking, a value for a capacitance is equal to A epsilon over D. A is a cross-sectional area. Epsilon is the electrical permittivity, which is given as epsilon naught times epsilon r. Epsilon naught is the absolute permittivity, and epsilon r is the relative permittivity. And D is the thickness of the electrical layer sandwiched by the two metals. So this is simply how you can calculate C. So the impact of C starts to be significant whenever it's associated with R, or a resistance, or what we can call an RC circuit. So whenever we have such an RC circuit, this reflects the general concept of either charging process or a discharging process. As you can see here, this is the charging process associated with a capacitor connected seriously with a resistance, and we have a voltage supply here charging the current in this way, and this is the relation linking between the variation in the voltage or current with respect to time. Alternatively, once this voltage is short-circuited, then a discharging process occurs. And as you can see from the mathematics of this equations, you can follow these mathematics step by step, but you will find that in both cases, we have an exponential term here, e to the power negative t over RC and e to the power negative t over RC, where we have this RC as the constant, or what we can call the time constant. So simply, the charging or the discharging process is a concrete function in the multiplication factor R times C. That's why the value of the resistance as well as the value of the capacitance are extremely important in determining what we can call the time constant of our charging or discharging process. So as you can see, the factor RC is a key parameter in determining this delaying or what we can call charging discharging time. That's why we are going to consider such RC factor as a critical factor in our next slides. Okay, so what we call charging discharging time can be considered from a logic gate point of view as a delay. Let's see. This is already, I think we already considered this model some lectures ago, when we consider that by default, MOSFETs has what we can call a parasitic capacitance, either due to the oxide layer between the metal oxide and the substrate or the channel region, or due to the various p-n junction included, and that's why we consider these different types of parasitic capacitance in a MOSFET. So when we connect MOSFET together, for example, in order to do an inverter, which is the simplest logic gate we already studied one lecture ago, these connections additionally add a resistance in addition to the capacitance. And from this perspective, the RC perspective starts to appear in a CMOS technology. So we have a capacitance due to the MOSFET, and we have a resistance due to the connection or the path of connecting different MOSFETs in a chip. So, for example, this is an example for the basic inverter circuit. Here, this inverter circuit is or can be equivalent, the capacitance in this inverter circuit can be equalized as an input capacitance and as an output capacitance. We already have discussed this issue in the previous lecture. So during the operation of this inverter, as you already studied in the digital electronics, you know that either the PMOS will be on or the NMOS will be on. In this case, this PMOS or the connection between the drain and source is typically not a short circuit. It has some sort of a resistance. So this is a resistance value. And then we have this capacitance. So you have this RC path while the PMOS is operating. Typically the same, and we can consider it here as a charging path simply because here we have the VDD and here we have the resistance equivalent to the PMOS, and here we have the capacitance. On the other hand, once this PMOS is off and the NMOS starts to operate, then we will have this charging path connecting the capacitor, the resistance due to the NMOS, and the ground. So the CMOS technology or the gate technology can be simply considered here from the point of view of a charging discharging capacitor. And as we mentioned, this RC factor will produce a propagation charging discharging with respect to time, which we will consider it as a delay. So this is an example of how we can consider the delay here. So for example, here we can see this charging or discharging time, what we can call it as a T full or a T the raise time and full time in an IC chip. So this is of course in the clock. So as you can see, if this is a V input and this is a V output, so supposedly if we are working in an ideal manner, so the V output should be identically equal to the V input, but due to this delay, we start to have this propagation delay, as you can see. So this propagation delay, it is a delay between getting an output and having an input. And as you can see in this delay, the logic gate does not perform its function as the input is high while the output is still high, which is not the typical case. After this propagation delay, the output will start to fall now into a low, as you can see. Here, another example, which is a reverse example, when the input starts to transfer from high to low. Again, it takes some time for the logic gate to consider this change, and typically there is also another sort of propagation delay, as you can see. Here, we call this as TP high and TP low, and TP high low and TP low high. So the the overall propagation delay simply calculated as the average between these two delays. The TP or the TP here, of course, stands for propagation, and here is high low, because the output is falling from high to low, and here from low high, as you can see. So this is the average between the average between the TP the average between the TP high low and the TP low high will result you an estimation for what we can call the TP or the propagation TPD, the propagation delay of a logic gate. So you can estimate the propagation delay using this value, and here you can find typical values for the TP low high and the TP high low from these equations. Of course, this is some sort of an empirical value, and again, as you can see, RP and RN, which are the resistance due to the NMOS and the PMOS, and CL, which is what we can call the load capacitance or the equivalent capacitance in the output, are a very significant factor in determining TP high low and TP low high. So these are a very considerable parameters in the evaluation of the propagation delay. We already have discussed in the previous lecture that the capacitance value is a very a concrete function in the W/L ratio, and this is simply considered from this equation. So you can never eliminate or remove the effect of the propagation delay. However, you can just play with adjustments. This can be through the W/L factor or even from the VDD factor. However, you can see that this equation or this proportionality is somehow against technology, because usually whenever we are going into technology, we are seeking for a lower VDD and a lower W/L ratio, and that's why maybe theoretically you can reduce the capacitance value, but whenever it comes to technology, it is not so easy to reduce the capacitance value. Okay, so here there is a very important point we already discussed in the previous, maybe in the previous lecture. We have already highlighted in a quick manner, but I feel it's now more appropriate to consume some slides dealing with this process or this concept, let me say, which is what we can call the sizing concept. And the sizing is simply how you are going to size your transistors. And let's start the process from the beginning. Why we need sizing? Why we should size our transistors? The answer is simple. In order to have this synchronization process between the NMOS and the PMOS transistors, they both have to be on the same hand or the same capability. But when we go to this very famous equation describing the current with respect to the basic voltage of VGS and VDS, and there is a term here which is most likely in your previous courses, we consider that this term is some sort of a constant term, which is Kn dash W/L. This term actually most of the time you consider this term as a constant, but now it's the time to consider it somehow an important term, because for transistors in general, when we have a constant biasing conditions, then most likely this term will be the same, which is the VGS, V threshold, VDS. So if we have the same V threshold, if we have the same VGS and the same VDS, so most likely this term will be the same. But what about this term? This term K dash W/L. W/L are geometrical parameter representing the width and the length of the channel, but Kn dash is a material parameter, and here it depends on the type of the material course of the MOSFET, as well as the type of the carrier moving. You know that MOSFETs are a unipolar devices instead of the bipolar transistors, where both electrons and holes contribute to the overall current. But here in the MOSFETs are a unipolar devices. That means that you only have either electron moving or holes moving. That's actually the difference between the N-channel MOSFET and the P-channel MOSFET. And here, when we go into the variation between electrons and holes, maybe we have to recall our solid state electronics basics, considering the mobility of electrons and the mobility of holes, that typically in silicon technology, which is of course the most famous technology. So in this technology, the mobility of electrons is roughly 2 to 2.5 times the mobility of holes. It's typically 450 to 1,350. So it's more than double the mobility of holes. So in order to make this compensation between holes and electrons, we have to compensate this in the term. So Kp is smaller than Kn. So in order to make the term W over L, K dash W over L, in order to make this term equally in both sides, what you can do simply is that you can compensate this variation or this difference. You can compensate this difference in the W over L. So instead of having, or if you have a W over L for an MOSFET, then you have to have double this value, which is 2W over L for the P MOSFET, so that you can compensate the difference in the Kn and the Kp. And this is simply the concept beyond the sizing process. So the concept beyond the sizing process is the process of how you can manage the W over L ratio of a MOSFET in order to equivalent the N MOSFET and the B MOSFET. And as you can see here, for example, you can have this ratio equals to 2 to 1. So this 2 to 1 for the 2 for the PMOS and 1 for the NMOS. And here you can see this relation that K and W and KP over WP. If W 2 WN equal over the WP equal, this is a ratio between WN and WP, as you can see. And in this case, you can somehow compensate the variation or the difference between the hole mobility and the electron mobility of your devices, which is again part of the nature of the silicon material, which you cannot change. So we can do a similar process when we consider other logic gates, and this is very interesting, by the way. So this is a very simple process when we do it for an inverter, because simply you have one PMOS inverter, one PMOS transistor and one NMOS transistor. But what about having different or other types of logic gates where we have more PMOS and NMOS transistors? So this is what we are going to do here in this slide, how we can size other logic gates as well. So, okay, let's do it now for other circuits as well. For example, here we have a very famous NAND gate. We already considered this NAND gate in the previous lecture, but from a capacitance perspective. But let's do it now from a sizing perspective. The process is very simple. When you have parallel, I think we can summarize in these two sentences. When you have parallel transistors, then you can consider that any one of them is working at the time. So you don't need to make any change in the ratio. So it will be the same. But when you have them in series, then the length is increased. So this affects the denominator of the equation or the ratio W over L. In other words, let's see. First of all, let's agree that we have to have, or we have to fix this ratio, which is 2 over 1 ratio. We have to fix this ratio all the time. I mean, the overall ratio of the N of the P is double that of the N generally. So for this NAND transistor, For this NAND transistor, we have two PMOS transistors, or for this NAND gate, I'm sorry, we have two PMOS transistors. So in parallel, nothing has to be changed. So this 2 will be directly converted to 2 and 2. Nothing will change because simply parallel transistors are not going to affect the overall length of the process. L is kept the same, so W over L will keep the same. One of them will work at a time. Either the current will either go to this or this. In both cases, it will see the ratio 2 over L. However, 2W over L, of course. However, here we have two of them connected in series, which means that the overall length is double. So in order to make an equivalent of 1, you have to have 2 here and 2 here. So this will be 2W over 2L, and this will be 2W over 2L. That means that the overall is W over L. This is simply how you manage this your transistor, because now you have a double length. So it's like you are making half plus half. So just see this number as 1 over to make it very easy. So I need to make this equivalent to 1. Okay, great. This is 1 over 2 over 1 over 2, and put these two here as your sizing parameter, and here 2 and 2. So applying the same on NOR, now you have series. You need to make this equivalent to 2. So think about the denominator. So 1 over 4 and 1 over 4. 1 over 4 plus 1 over 4 equals 1 over 2. So the equivalent here will be 2. However, here we have two parallels, so we have to keep it at least 1 as it is. So this is an example for that. So let's do it here, for example. Again, very easy. Now, your path can be in this direction. So in this path, this will be 4, and this will be another 4. So 1 over 4 plus 1 over 4 gives you half, which is you have 2 here. But if you go to this path, so these two transistors in series should equivalent to this one. So 1 over 8 plus 1 over 8, which is 1 over 4. So again, whenever it's parallel, think about the denominator. So 1 over 8 plus 1 over 8 equals 1 over 4. Then 8 times 8 and 8, and this 4. This is the equivalent. On the other hand, this is a lone transistor, so you have to have it 1, and this is the equivalent. So it can be either in this path or either in this path. In both cases, we have two transistors in parallel, and we need that the overall of these two transistors to be 1. Think about the denominator. So 1 over half plus 1 over half equals to 1. So it's 2 and 2, 1, 2 and 2 equals to 1. So you can make it very easy. Another example, let's see this example. This is a very straightforward example again. So this will be what? This will be typically 2, because this is an alone transistor in the PMOS track. And the equivalent of these 3 should be again 2. So you have to have these 3 transistors equals to 2, which is 6 plus 6 plus 6. So if you can make this 6 plus 6 plus 6 plus 6, then you will have this equivalent of 2. Simply, if it's 1, it will be 3 plus 3 plus 3. We multiply it by 2. That's why it's 6 plus 6 plus 6 to have an equivalent of 2. And then in the other way, or in this direction, we have 3 parallel, 2, 2, 2, and this is a common 2. So if you go through this path, half plus half is equals to 1, half plus half is equal to 1, half plus half is equals to 1, and so on. So you can fix this sizing process whenever you are doing any sizing process. You can make it in this manner. Another very simple example. I think this is a very simple example. Here we have 2 transistors. So here we have an overall of 2L, and we need to make the overall W over L equals to 2. So if you have in the denominator 2L, you have to have in the numerator 4W. That's why we have 4, 4, 4, 4. Now, in the other hand, if you have in the numerator 2L and you need to have a W over L ratio equals to 1, then you have to have the W equals to 2. That's what you have 2, 2, 2, 2, and so on. So this is simply how you can size. And as you know, this sizing process will affect the overall capacitance seen by your transistor. We already discussed, or by your gate, we already discussed this process in the previous lecture. So simply, when we consider the capacitance in a transistor, in a logic gate, we are considering the overall output and the input capacitance. Of course, the input capacitance for one gate will act as a load capacitance for the previous gates. That's why the input capacitance, by the way, is important. But now for this capacitance concept, the value of the capacitance will attribute to this overall delay seen by the gate. So this is a very simple equation that you can use. So the higher the CL, the higher the TP high low and TP low high, and then the higher overall propagation delays. That's why you can consider this sizing process is a very important process that affects the overall sizing, the overall propagation delay of a logic gate. Okay, that's very interesting so far. Let's go to another small topic related to the fin and the fin in and the fin out. So what is the fin in and fin out? Fin out refers to the number of gates and output connected to. So how many gates you are connected to? For example, here we have a fin out of 1, and here we have a fin out of 3. As the fin out increases, CL will goes up proportionally, and means that the delay increases. This is very important because, as I just mentioned, the input capacitance for your gate is a load capacitance for the previous gate. For example, in the figure above, here, your output capacitance is mainly driven due to the input capacitance of the next gate, which is this one. Here you have three logic gates in parallel. These three logic gates connected will mean that simply, if we say that we have generally an CL capacitance, and in this graph we have 3 CL, which means proportionally 3 times the delay. That's why the fin out is a very important parameter in your design. Increasing drive strength. So we have always modeled an ideal inverter for our transistor. So this is an ideal transistor with ratio 1:1 for the MOSFET and 2:1 for the PMOS. We already consider this in very detailed manner, either in this lecture or the previous one. So this, how you can see the variation in the capacitance. So here we are just expressing that once you go for more and more sized transistors. So for example, I can say that instead of I making W over L1 and W over L2 for the NMOS and PMOS, I will make it 4 and 8. Logically speaking, this is acceptable because the ratio is half. The W over L for the PMOS is 8 W over L, and the W over L for the NMOS is 4 W over L. That's great. So logically, it will work. But what will happen simply here is you multiply the overall capacitance seen by the inverter times 4, which will attribute to the overall propagation delay in this step. So this is a very important one. Another important parameter is the fin in, refers to the number of inputs in the gate. Here you can see. So each input adds its intrinsic parasitic capacitance. Simply, each input has its capacitance. So the overall propagation delay will be the summation of the overall capacitance seen by all these parameters. So this is also a very important parameter related to the effect of the fin in your design. So simply, we can say that these are what we can call delays associated with the logic gates, either from the input terminal or from the output terminal. From the input terminal here, let me go back to this important slide, I think. Yeah. So from the input terminal here, you have an input capacitance which will affect this TP high-low value, and the higher the fin in, the higher the TP high-low values. And from the output perspective, you have this output capacitance that affects the TP low-high value, and the higher the fin out, the higher the TP high-low value, and generally then the higher the propagation delay, which is, of course, a problem. So this is one type of delay that can see in your digital electronics IC, but still there is some other sort of delays, which is the interconnect delay. So what is the interconnect delay? Simply, it's a very basic related to how you are considering the wiring between gates, because simply we have to connect gates and terminals using wires. So ideally, we consider these wires are with zero resistance value, so no voltage drop, no effect. When we go from a wire to from a node to a node, we even in circuits we consider it one node whenever you have a wire. But realistically, this wires has some sort of resistance, simply because it's a material which is, of course, not a superconductor. It's a real material with a given resistivity or conductivity. There is a length, and the higher the length, the higher the resistance. And this is a cross-sectional area, which is a very critical parameter here, because the lower the cross-sectional area, the higher the resistance. So when you scale down your technology using the Moore's law, you should expect higher and higher resistance due to the interconnections. And this is very important. So long paths and higher and smaller cross-sectional area is typically results in higher resistance. And here is a very important parameter considering the effect of the interconnection in adding also delay, not only resistance. So another important factor here is this lumped model equivalent to a resistance in the capacitor seen by the interconnection between gates. And this will again contribute to the overall RC or the overall delay seen by your chip. So whenever we are doing this designs, we have to consider that we still have some sort of delay due to the interconnections. Of course, you can manage to minimize this delay in order by shortening the distance of these interconnections, so that because usually cross-sectional is not a very adjustable parameter in the design, simply due to this is related to the technology of fabrication, but the distance between gates, or I mean the wiring between gates, is some sort of the routing, which is part of the layout process. So as a designer, you should act to shorten this distance in order to minimize the interconnection delay effect. Let's go to the final stage of this lecture related to what's called the power dynamics. We can consider that part of the problem related to the, of course, delay is an important problem related to the parasitic capacitance in the logic design or the digital design. But actually, the delay is not only, or is not the only problem associated with this. There is also another problem related to power, because the dynamic motion from high to low and from low to high definitely consumes power, which should not be consumed. Simply, if you go to this, again, critical slide here, ideally speaking, this signal should go directly to low in this stage. So due to this propagation delay, some more additional power has been consumed by the circuit that should not be consumed. So this is what we can call a dynamic power. So simply, the dynamic power can be calculated with this relation, as it's half C total, which represents the total capacitance seen by the circuit, VDD F square, where F represents the clock frequency. So you can see from this equation two extremely important factors. The first is, which is a very logic conclusion, the higher the capacitance, the higher the power dissipated, or the higher the dynamic power dissipated in your chip. But Another important process is if we keep the same circuits, the same total capacitance, but due to the technology, we scale down the technology. I mean, we speed up the clock frequency. Even this will result with a high dynamic power, with square relation, with a direct relation with the frequency. So this is very important. VDD, the supply voltage, the total capacitance seen by the chip, and the operating frequency of the clock. These three parameters attribute to the total power, dynamic power consumed, which is, of course, something not preferable to be high in your digital IC design. Thus, my dear students, conclude not only the part of this lecture, but also the overall course of our selected topics, where we have discussed together various technologies, a mix of technologies between basic analog design, sensing, nanosensing, biosensing, RF design in a form of detuned amplifier, parasitic capacitance, VLSI technology as an introduction, CMOS technology in terms of inverters, parasitic capacitance in digital IC design, and propagation delay. I hope that you have learned some concepts from this that can really reflect it for your next career, inshallah. Thank you very much for your concentration. Maybe see you in next courses, inshallah. Most likely postgraduate courses. Thank you very much. See you later on.